Thanks for coming to my talk. I'm Rohit Dhariwal, and my advisor is Dr. Sharma Rani. And the topic of my presentation is effects of forcing scheme on the flow and the relative motion of inertial particles in DNS of isotropic turbulence. So the outline of my presentation is I'll start with the motivation for the current problem, describing some natural and industrial applications where my particle intermittent flow research is applicable. And I will also mention some key statistics, and then I will describe our analytical work in little bit detail, followed by the parallel performance of our DNS code, and in the end I will discuss the effects of forcing scheme in DNS on motion of inertial particles. Okay. So the problem we are looking at is particle intermittent flows. So particle intermittent flows are important both in natural as well as in engineering applications, such as in warm cloud precipitation, where atmosphere scientists are investigating if the turbulence augments water droplet growth rates by increasing droplet collision rate, which may hasten the rainfall initiation. And the second application is planetesimal formation, where the astrophysicists are interested in knowing if the various turbulent division mechanisms such as dispersion, sedimentation, collision coalescence impact the planetesimal formation. Another application of particle intermittent flow is in volcanic eruption, where understanding dispersion of volcanic particles in atmosphere is of interest. And in industrial application is in spread dynamics in engines, where the effect of turbulence on atomization, dispersion, and evaporation of fuel droplets is a relevant physics. In all the above mentioned applications, we are basically interested in quantifying the effects of turbulence on particle pair relative motion. So let me describe what do we mean by particle pair relative motion. So particle pair relative motion refers to the temporal and spatial dynamics of pair separation r and pair relative velocity u. As we know, turbulence is known to spatially homogenize passive scalar, but in the case of inertial particles, it introduces strong inhomogeneities both in spatial as well as in the relative velocity domain. The spatial inhomogeneities are basically quantified by a statistics known as radial distribution function, which is shown by the preferential concentration of particles in specific part of the flow field domain. And relative velocity inhomogeneities are shown by the non-Gaussian relative velocity PDFs of the relative velocity PDF P of u sub r, where u sub r is the component of relative velocity along the pair separation. And both these statistics of basically RDF and PDFs are used as an input to compute the collision frequency, which is given by this expression. Now let me describe particle preferential concentration. So particle response to turbulence is basically controlled by its inertia, and it is quantified by a non-dimensional number known as Stokes number, so which is given by the ratio of particle viscous relaxation time to a flow scale time scale of interest. And it has been observed when the Stokes number is less than or of the order of 1, the inertial particles accumulate in the region of high strain region over the high vorticity region, which is shown by this diagram over here, where we can see the highly inertial particles are ejected out of the high vorticity region into high strain regions. And this preferential concentration can also be quantified, as I described earlier, by statistics known as RDF. So here we are showing the work of Reed and Collins, where they demonstrated the effect of Stokes number on preferential clustering. In their study, they considered 6 different Stokes numbers. So Stokes number of 0.01 basically means particles have very less inertia, so they will try to follow the fluid particles, or basically known as tracers, very closely. But as we increase the Stokes number, particle inertia will increase, and they will not follow the fluid particle very closely. And we can see that for Stokes number of 0.01, inertial particles are almost uniformly distributed throughout the whole domain. But as we increase the Stokes number, the preferential particles start to preferentially concentrated in certain region of the domain, and we can see that the preferential concentration increases with Stokes number, and it is maximum for Stokes number of 0.7. And if we increase the Stokes number further, particle preferential concentration decreases, and they start to become again more uniformly distributed throughout the whole domain. And here in the plot on the right, they are showing the residual RDF, which is basically RDF minus 1. So RDF of 1 shows that the particles are uniformly distributed throughout the whole domain. And if the value of h of r is greater than 0, it will mean that the particles are preferentially concentrating into certain parts of the domain. So here they are showing the residual RDF as a function of pair separation r. And here they are showing 5 Stokes number, and we can see that the preferential concentration at small pair separation is maximum for Stokes number 0.7, and it decreases as we further increase the Stokes number, which is exactly shown in this diagram as well. So next statistic of interest is pair relative velocities. And in the DNS study by Sundaram and Collins, they illustrated that the nature of relative velocity PDF changes with the pair separation. So the pair relative velocity is Gaussian in nature at large pair separation, and it becomes more and more non-Gaussian as the pair separation decreases. So the particle pair relative velocity is Gaussian in nature at large pair separation because particles effectively become uncorrelated at very large pair separation, and as we decrease the pair separation, the relative velocities become correlated. So therefore, any analytical model which try to capture the relative motion of inertial particle should be able to capture both these trends in preferential concentration as well as in the pair relative velocity. Now let me describe a little bit about our analytical work. In a recent study, we derived a closure form for the diffusion current in the PDF transport equation for the relative motion of high Stokes number particle, which is given by this. This is the PDF transport equation, omega of r comma u, where r is the pair separation and u is the pair relative velocity, and duu is the unclosed diffusivity tensor for which we derived an analytical closure form. And for the limit of str much greater than 1 particles, where str is a Stokes number based on time scale of eddies whose size scales with particle pair separation r, which is given by this expression, where this is the Eulerian 2-time correlation of fluid relative velocity at particle position, where delta u is also known as seen fluid velocity, or in simpler terms, the fluid velocity at the particle pair locations. And since we are considering very high Stokes number particles, so the particles are effectively stationary over the flow timescales. So therefore this correlation is basically Eulerian 2-time correlation. Now this Eulerian 2-time correlation can be computed 2 ways. First is we can compute this correlation using direct numerical simulations, but these correlations are computationally very expensive, and at that time we did not have enough computational resources to compute these correlations using DNS. So what we did, we derived an closure form for this diffusivity tensor by converting these 2-time Eulerian correlation into 2-point correlations in the limit of very high Stokes number. So why blue waters? So the reason for using blue waters is the early compute resources we had on XSEED as well as on Alabama supercomputer were not large enough for us to compute these Eulerian 2-time correlations. But the allocation on blue waters made it possible for us to compute these Eulerian 2-time correlations. So the 2 important parameters for these Eulerian 2-time correlations are number of pairs we consider, and second, the pair separation we consider to compute these Eulerian 2-time correlations. And for obtaining this Eulerian 2-time correlation, we consider almost 500 billion of stationary particle pairs, and the pair separation. So we have to divide the whole particle pair separation to small bins, and so but in order to obtain a sufficiently large pair separation, there are 2 competing effects. First is how big this pair separation should be, and So if the pair separation is too big, we won't be able to capture the particle which have small Kolmogorov length scale separation. But if, and on the other hand, if we use the particle bin size too small, then we will have statistical noises. So after performing several iterations of several different number of particle pairs and different bin sizes, we found out that the bin size of Kolmogorov, 1/8 of Kolmogorov length scale was sufficient enough for us to obtain smooth statistics. And these statistics were the correlation were computed using 20,000 processor on blue waters. Let me try to tell you like how this computation expensive. So in order to compute this product of fluid relative velocity at particle locations over all the half of the trillion pairs and having a time separation of tau, it required us 40 hours of wall clock time to compute over all the half a trillion pairs for a given time separation tau. And we similarly use 200 of such tau pairs to get one average value. So this was computationally pretty expensive task. So here are the Eulerian two-time correlations obtained using the previously mentioned DNS simulation. So here we are showing the longitudinal and transverse component of the Eulerian two-time correlations at 3 pair separations of R by L of 0.2, 0.5, and 1, where R is the pair separation and L is the integral length scale. And we are showing them as a function of T eddy, where T eddy is the integral time scale. So after computing the diffusivity tensor, we performed Langevin simulation using this diffusivity tensor to see how good our analytical closure is as compared to the DNS simulations. So here we are showing RDFs as a function of Stokes number at a Reynolds number of 131. So the squares represent the RDF obtained using our analytical closure, and the circles are obtained from our DNS simulations. We are also comparing our results with the DNS work of Favre et al. And also with the theory of Jechik et al. And we can see that our current theory is able to capture the RDF trends very well at 2 different pair separations of R equal to 6 eta and at 18 eta as well. Now let me describe our DNS code. So the governing equation for our DNS code are basically the same continuity equation and Navier-Stokes equation in rotational form, where F sub F is the external forcing to maintain a statistically stationary turbulent flow. So our code is basically pseudo-spectral, and we use RK2 as the time step marching scheme. And the FFTs are performed using the P3 external library P3D FFT. And the particle phase governing equation are these 2 governing equations, where V sub P is the particle velocity, and U x of P comma T is the fluid velocity at particle location. And since the particles can be anywhere in the domain, so we have to interpolate the fluid velocity at particle locations, which is done by using 8th order Lagrangian interpolation. So initially our code was 1D parallel decomposed, which basically means our cubic domain of 2 pi length in each direction was divided into was decomposed along one direction. So here we can see that it is decomposed along y direction. So we have slabs in x and z axis, and in the second figure we are showing the decomposition along x axis. So but the limitation of this kind of parallel decomposition was we could only run our simulations of n cube grid points only up to n processors, and which limits us to perform high DNS simulations. Therefore, we implemented a 2D domain decomposition in our DNS code, which is basically decomposing along 2 directions. Now instead of slabs, we have pencils, and we have each process has like data local along one direction locally. So what it does is it allows us to perform n cube grid simulations on up to n squared processors, which as a result will allow us to perform higher Reynolds number, higher DNS simulation, and as a result achieve higher Reynolds number. And so here is the scaling of our 2D parallel code, and we can see that we have been able to achieve reasonably good scaling up to 60,000 processors, and we are still working on improving our scalability of our code. Now let me describe the final part of my talk, where I will describe the effects of forcing schemes used in the DNS simulations on the motion of inertial particles. So recall in the Navier-Stokes equation I showed, there was a forcing term called FF, which basically maintains statistically stationary turbulent flow. So this large-scale forcing can be applied in two ways. The first is called as deterministic forcing, where the turbulent kinetic energy dissipated during a time step is added back to the large scales of the flow. And the second one is the stochastic forcing, where random forcing acceleration based on Ornstein-Uhlenbeck processes are added to the velocity components. And there are two important parameters in stochastic forcing. One is acceleration variance, and second is the forcing time scale. So in our study, we are currently considering three different grid resolutions to study the effect of forcing time scales. First is 128 cube, second 256, and 512 cube. And the Reynolds number we are trying to achieve here are 76, 131, and 196. And Reynolds number are based on Taylor micro length scale. And we are trying to here, instead of just limiting ourselves to large Stokes number, we are trying to consider the whole range of Stokes number, ranging from 0.05 to 40, so that we can see the effects of large scale forcing on small as well as highly inertial particles. And the number of particles for different grid resolutions is varying from 262,000 to 2 million particles per Stokes number for 512 grid simulations. And in our study, we are considering 5 different forcing timescales, which range from TE by 4 to 4 TE, where TE is the large, which is eddy turnover time obtained from our deterministic run. So now let me show you some preliminary results. We have only been able to do post-processing of 128 cubes so far, and 256 and 512 is still going on. So here we are showing the RDF as a function of Stokes number for Reynolds number of 76, and the Stokes number range we are showing here is 0.05 to 1. And we can see that at really small Stokes number of 0.05, the RDF obtained from all the different forcing schemes and deterministic forcing are almost on top of each other, which is expected because we are imposing large scale forcing, and we expect it won't affect the small scales, and which in turn, and as we know that the low Stokes number particles are affected by small scale of the turbulence, so therefore we expect all the forcing schemes to give good agreement in RDF at small Stokes numbers, and which is we see at both small separation of 0.1 as well as and Kolmogorov length scale. The small separations of 0.1 and eta are important to us because these separations will help us to compute the collision kernel more accurately. So second, we are showing here the RDF as a function of Stokes number for Stokes number varying from 1 to 40. And we can see that at really large Stokes number, again, all the RDF predicted by all the different forcing schemes are on top of each other, which is again expected because when the particle inertia become too large, it is not affected much by the large scale of the flow. And the Stokes number we are considering is 40, so whose time scale are even bigger than the largest flow time scales. So that's why all the forcing schemes are showing RDFs right on top of each other. So in conclusions, we computed our analytically closed diffusivity tensor using DNS, and the pair statistics obtained using our analytical model is in very good agreement with the DNS results. And we are also currently studying the effects of forcing on the relative motion statistics. And for the future work, we will try to improve the scaling of our code further and perform 1024 and even larger DNA simulations. So thank you.